Okay, today we'll be talking about the handling of bicarb. First of all, we'll have a quick recap on our acid and bases. An acid, as we know, is an ion that donates hydrogen ions as well, and a base is a compound that accepts them. In the human body, the neutral pH range is from 7.35 to 7.45. Anything above would be alkalotic, and anything below would mean the patient is acidotic. It is not at at our normal 7 because the temperature is of the body is not at standard lab condition of 25. Therefore, the exact neutral point of the body is 7.4. Volatile acids in the human body are those that are excreted by the lungs, and thus they are CO2. In the normal human body, the human body excretes approximately 13,000 millimoles of acid a day through the lungs, and as such, you can tell that our lungs are very good at it. The equation that dictates the acid-base equilibrium within the body is as follows. CO2 combines with our water to form our carbonic acid, which then dissociates into our bicarbonate and hydrogen ion. And as we all love and all remember of chemistry from year 12, we know our Le Chatelier's principle, in that an equilibrium equation will shift in the direction that counteracts a change that is introduced. As such, an increase in CO2 when not excreted will result in a leftward shift, causing increases in bicarbonate and our hydrogen ions, and vice versa if there was an increase in hydrogen ions. If the body is unable to manage these changes in hydrogen ions, this would lead to the person becoming acidotic or alkalotic if the lungs were unable to function, which would be deadly. Non-volatile acids are all acids produced in the body that are not excreted by the lungs. This is due to them being produced from metabolic waste and the breakdown of other compounds. As these cannot be expired, they must be counteracted via buffering. Approximately 70 millimoles of non-volatile acids are produced daily and thus required to be buffered or would lead the patient to become acidotic. So how exactly is this done? So bicarbonate is responsible in counteracting the pH changes caused by the production of acid via neutralization. However, as a consequence of buffering, there is also a loss of bicarbonate, in which if it cannot be regained via reabsorption, such as in expiration, it must be regenerated or created to replenish what is lost. So first of all, how is bicarbonate resorbed? Well, it is resorbed in the proximal convoluted tubule, ascending limb of the loop of Henle, and the distal nephron. It is freely filtered via the glomerulus and thus dumped directly into the Bowman's capsule, and therefore must be extracted back out of it to get back into the body. In terms of what exactly happens, carbon dioxide and water freely diffuses across the apical surface of the lumen into the epithelial cells of the nephron, where carbonic anhydrase forms with the compounds of carbon dioxide and water to form carbonic acid, which then dissociates into our hydrogen ion and bicarbonate ions, which is then actively transported out of the cell and into the blood via the basolateral membrane, whilst the hydrogen ion that is left is pumped back into the lumen of the renal tubules to combine with free bicarbonate ions spontaneously to form carbonic acid, which is then broken down by another version of carbonic anhydrase that is present on the apical surface of the epithelial cells to form our water and CO2, and thus the cycle continues until all the bicarbonate is resorbed back into the blood, or what is left, and can be reabsorbed back into the blood. Now we'll look at the regeneration, also known as the creation of new bicarbonate. And it occurs once almost all bicarbonate has been reabsorbed, as inevitably some bicarbonate is unable to be reabsorbed back from the tubular fluid due to it being too tightly bound to other compounds, or there just being not enough time or not enough molecules present for it to combine and form carbonic acid and be reconverted into our bicarbonate ions. In this case, bicarbonate is formed in the cell similarly to the process of reabsorption of bicarbonate. However, in this instance, a hydroxide ion does not come from the tubular lumen. Instead, it comes from the breakdown of other metabolic compounds which contain hydroxide ions. An example of this is from the breakdown of glutamine. Excess hydrogen ions that are produced in this process are then excreted back in the tubular lumen and buffered by other ions present in it.